if you strip away all the hype,
All the sci-fi stuff.
right, all the science fiction, and the really confusing jargon that surrounds modern artificial intelligence today, you're actually just left with 3 massive industry-level engineering problems.
Just 3.
That is literally it. Just 3 fundamental hurdles that absolutely must be cleared if you want to build any functioning modern AI system.
Mm-hmm.
First problem, how do we actually represent human language as raw numbers so that a machine can even begin to process it?
Because they don't speak English.
Exactly.
Yeah.
Second, once we actually have those numbers, how do we get the machine to understand the rich context and, the subtle meaning behind them?
The tricky part.
Yeah. And third, once the machine has this supposed intelligence, how do we serve it to real users, reliably, out there in the messy real world? Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
And for today's deep dive, we are really pulling from a huge stack of architectural breakdowns, API documentation, and foundational research to entirely demystify these systems.
That's a lot of material.
It really is. And, the leap from traditional deterministic coding to the kind of probabilistic nature of machine learning, it can feel like stepping onto another planet.
Oh, absolutely.
But when you actually dig into the engineering logic under the hood, it truly just boils down to solving those 3 exact problems you mentioned.
Right. And to just set the stage for you listening right now, we kind of already know your background.
Mm-hmm.
You most likely have a solid working understanding of Python.
Mm-hmm.
You know how to write scripts. You probably use loops. You manage state with variables, and you're very comfortable with dictionaries and lists.
Standard Python stuff.
Yeah, standard stuff.
Mm.
But stepping into the machine learning space often feels like you're hitting this massive brick wall of terminology.
Yeah, totally.
You start hearing terms like embeddings and transformers and model drift, and it honestly sounds like a completely alien language.
It's intimidating.
So our mission today is to translate that alien language into the plain engineering logic that you already know.
And to do that effectively, we really need a master framework. Right. Like an overarching mental model for the entire architecture we're dissecting today. Because if you keep this specific framework grounded in your mind, every technical paper you read and every single API endpoint you hit later on will actually make logical sense.
So what is that framework?
It is entirely sequential. Represent, understand, and serve.
Represent, understand, serve.
Exactly. First, we have to represent the input data mathematically. Then, the architecture has to process and understand the relationships within that data. And finally, we have to serve that computational output as a reliable product.
It's a straight pipeline.
It is an unbreakable pipeline. Represent, understand, serve.
Okay, let's dive right into breaking down that pipeline, starting with stage 1. Represent.
The foundation.
Right. We're talking about the fundamental conversion of human language into raw mathematics. Because computers, at their absolute core, are just highly complex calculators. They don't process English or Python natively. They process electrical signals that we, abstract into ones and zeros.
Right.
So the very first non-negotiable step in any AI pipeline is converting a string of text into a mathematical format. And the first concept for this is tokenization.
Yes, tokenization.
But, from a Python perspective, isn't that literally just using a dot split method on a string to break a sentence into a list of words, like text.split?
It is really tempting to think of it that way, but dot split is just way too simplistic for what modern AI requires.
How so?
Well, think about it. If you just split by spaces, you run into massive inefficiencies immediately. What do you do with punctuation?
Oh, right. A word with a comma attached becomes a completely new word.
Exactly. Or what do you do with a compound word or a typo? If the model hasn't seen that exact misspelled string before, it just breaks, doesn't know what to do.
So what's the alternative?
Modern systems use much more sophisticated algorithms. Byte pair encoding is a major one to perform this tokenization.
Byte pair encoding.
Yeah. Think of it like breaking a massive, complex Lego structure down into highly reusable, standardized little Lego pieces.
So it's not strictly breaking things down word by word at all.
And far from it. When an AI ingests the string "I love machine learning," it doesn't necessarily see 4 distinct words.
Okay.
It sees a sequence of smaller, machine-readable chunks called tokens. Now, sometimes a token is a full common word, like the word love is probably just one token.
Because it's so common?
Right. But for longer or more complex words, the tokenizer might split it into syllables or phonetic chunks.
Give me an example.
Okay, take the word unbelievable. The tokenizer might chop that into unbelieve and able.
Oh, I see. 3 separate tokens.
Exactly. And by breaking human language down into these foundational Lego pieces, we create a fixed, finite vocabulary. Usually it's around maybe 50,000 to 100,000 distinct tokens.
So every piece of text ever written can be constructed from this finite box of 50,000 Lego pieces.
You got it.
That fixed vocabulary is super key. So in Python terms, you are basically taking an infinite possibility of user string inputs, and you're mapping them to a predefined dictionary where every single token has a specific integer ID.
Yes, exactly like a dictionary lookup.
But wait, an integer ID, like say token number 4502, that still doesn't tell the computer what the word actually means.
Not at all.
It's just a meaningless label in a lookup table.
Yeah.
So how do we actually take those integer IDs and map them to real semantic meaning?
Well, here's where it gets really interesting.
Okay.
This is where we introduce the second core engineering concept, embeddings.
Embedding.
Yeah. To conceptualize an embedding space, I want you to imagine a vast, highly dimensional mathematical map.
Like a GPS map.
Kind of, but we are not talking about a flat 2D map. We are talking about a mathematical space with thousands of dimensions. Yeah. And every single token from our predefined dictionary is assigned a permanent location, a coordinate on this map.
Okay.
And the brilliant insight here is that the coordinates are not assigned alphabetically. They aren't random. They are assigned strictly based on semantic relationships.
Meaning words that share contexts or meanings live in the exact same neighborhood on the map.
Precisely. Dog and puppy live right next to each other. Dog and refrigerator live miles apart.
Let's ground that in code for a second. If we are plotting coordinates, we are essentially building a NumPy array of floating point numbers for every single token, right?
That's exactly what it is. A vector, in this context, is simply a long list of numbers, an array.
How long of a list?
In a modern model, that array might contain something like 1,536 floating point numbers.
Wow.
Yeah. That single array represents the exact pinpoint coordinates of where that specific token lives in our massive multidimensional map.
That's dense.
Very. And the geometry of the space is just staggering. Because the map is organized strictly by meaning, you can actually perform real mathematical equations on concepts.
Wait, math on concepts, like adding words together?
Yes. The classic example in the research is vector addition and subtraction. If you take the massive coordinate vector for the token king,
Okay.
you subtract the vector for man, and you add the vector for woman.
You drop right onto the vector for queen.
Almost exactly on the exact coordinates for queen.
That is wild. So an embedding is really just the computational process of taking our integer Lego piece token, looking up its 1,536 dimensional coordinate array, and feeding that giant array into the system.
You've got it.
So we've successfully taken language, chopped it into tokens, and translated those tokens into complex numerical arrays that represent true semantic meaning.
The represent stage is almost done.
But here is the massive bottleneck that I see developers run into all the time with APIs: hardware limits. If we are converting every single word of, say, a 500-page book into a 1,536-dimensional array of floats, the sheer amount of RAM required to process that simultaneously must be astronomical.
It's massive.
Why can't the AI just process an infinite amount of text at once?
That completely comes down to computational scaling, and it introduces our third concept for today, the context window.
Context window.
Yeah. To visualize this, I want you to imagine the AI has a physical workbench or a memory desk where it performs its active calculations.
Okay, a desk.
This desk has a rigid physical boundary. The AI can only fit so many of those embedded token arrays on that desk at one time before things literally start falling off the edge.
Okay.
That available surface area, that is the context window. It is a hard physical limit on the number of tokens the architecture can hold in its active working memory during a single operation.
So when developers complain that an AI chatbot suddenly forgot the specific persona they established like 20 minutes ago in the chat,
Yeah.
that's not a software bug, it's a hardware reality.
Exactly.
The conversation literally grew too long, and the earliest tokens that contain that persona instruction were physically pushed off the memory disk to make room for the user's newest messages.
That is the exact mechanical reality of what's happening. The data is simply no longer in the active matrix being processed. It's gone.
So naturally, you might ask, why not just build a bigger disk? Why not engineer an infinite context window so it never forgets?
The reason is that the mathematical operations the AI performs on these tokens, they scale quadratically, not linearly.
Quadratically,
Yep.
meaning it gets way more expensive way faster.
Right. If you double the size of the context window, the computational power required doesn't just double, it roughly quadruples.
Oh, wow.
The memory requirements just absolutely explode. Engineering larger context windows is literally one of the most expensive and complex hardware challenges in the entire field right now.
Okay, so that perfectly encapsulates the entire represent stage of our framework.
It does.
We take human strings, we tokenize them into integer IDs, we map those IDs to dense floating point arrays called embeddings to capture their meaning, and we load those arrays into the limited space of our context window. The data is now fully prepared.
Perfectly formatted numbers.
But preparing the data doesn't generate intelligence.
Right.
A dictionary isn't smart just because it contains words.
True.
How does the architecture actually look at that massive grid of floating point numbers on the memory disk and extract nuanced grammatical context?
This moves us firmly into stage 2 of our master framework, understand.
Understand.
And to explain how the system extracts context, we really have to look at the architectural breakthrough that defines this entire modern era of AI.
The big one.
It revolves around a mechanism called self-attention.
Self-attention. Let's break that down.
Think about how human reading actually works in your brain.
Yeah.
If you read the phrase, the bank of the river, your human brain doesn't freeze in confusion trying to figure out if the word bank means a financial institution like Chase or muddy ground.
Right, because of the word river.
Exactly, because as your eyes scan that sentence, your brain acts like a dynamic highlighter. It automatically highlights the word river and uses it to retroactively lock in the meaning of the word bank.
The surrounding words act as anchors for the ambiguous word.
Exactly.
But mathematically, how do you program a highlighter in Python?
You do it through massive matrix multiplication. Attention is the mathematical process of computing relevant scores between every single token on the memory disk and every other token on the disk.
Every single one.
Every single one. As the AI processes the data, it essentially forces each word to ask, how strongly do I relate to the words around me?
Okay.
So the token for bank mathematically compares its embedding vector to the embedding vectors of the and crucially, river.
And it calculates a high similarity score with river.
Right. Which dynamically adjusts the numerical representation of bank for that specific sentence. The token's meaning literally shifts based on its neighbors.
Hold on, let's contrast this with older machine learning technology to really highlight why this was such a massive breakthrough. Before this attention mechanism existed, how did older models try to read text? Were they just iterating through a list one item at a time?
They were, and it was a huge bottleneck. Older architectures like recurrent neural networks or RNNs process data sequentially.
Like a standard for loop in Python.
Exactly, like a for loop. It read token 1, then token 2, then token 3, strictly moving from left to right.
Which sounds logical.
It does, but imagine trying to understand a highly complex murder mystery book, but you are only allowed to look through a tiny keyhole.
Oh, wow.
You're panning slowly across the room, seeing exactly one clue at a time. It makes it incredibly difficult to maintain the context of clue A by the time you finally reach clue Z. You just forget.
Which brings us to the transformer architecture.
Yes.
If the old models were a for loop looking through a tiny keyhole, what is the transformer doing differently?
The transformer fundamentally shatters that sequential bottleneck. Instead of looking through a keyhole, a transformer processes the entire room all at once, in parallel.
Looks at the whole room simultaneously.
Yes. Because it is built entirely around that self-attention mechanism, it doesn't need to read left to right. It takes the entire array of tokens in the context window and computes the relationships between all of them simultaneously.
So when a research paper mentions a transformer model,
They are describing an architecture that leverages parallel processing and self-attention to instantly calculate the complex, overlapping contextual web of a sequence, rather than reading it word by agonizing word.
so we have the transformer acting as this parallel processing engine, running attention across all the embeddings. But the transformer itself is a type of neural network.
It is.
In traditional programming, we write explicit conditional logic. If this, then that. A neural network absolutely doesn't work like that. How should a developer visualize the actual structure that's doing this processing?
A neural network is best conceptualized as a deeply layered pattern extractor.
Layered pattern extractor.
Think of an assembly line where the product passes through multiple sequential stations. In a neural network, the data passes through multiple hidden layers.
What happens at the first layer?
At the very first, shallowest layer, the network might just be recognizing the most basic, rigid mathematical patterns, perhaps basic syntax or simple word clustering.
And then?
As that data is mathematically transformed and pushed deeper into the next layers, the network begins to extract higher-order concepts. It moves from recognizing just word pairs to understanding grammatical structures to eventually extracting complex tone, intent, and deep semantic nuance by the final layers.
So it's a hierarchical filtering system.
Exactly.
And the parameters that govern how those filters actually work, the actual variables holding the logic, are what we call weights.
Yes, weights.
Okay, let's unpack this, because this introduces one of the most critical conceptual hurdles for developers entering this space. The fundamental difference between the model's weights and the prompts we send it.
It's a huge point of confusion.
I see developers constantly trying to build complex Python scripts, thinking they are literally programming the AI with their prompts. What is actually happening under the hood?
Let's draw a strict hard line between the two right now. The weights represent the AI's actual permanent brain structure.
Permanent.
Yes. A modern model might have 70 billion weights. These are literal billions of floating point numbers distributed across the neural network that determine exactly how data flows from one layer to the next.
And how do they get there?
These weights were solidified over months of intense computational training. They are static, they are frozen.
Okay, so what is a prompt then?
A prompt is just a string of text you pass via an API call. Think of the weights as the deeply ingrained permanent knowledge of a PhD expert, and the prompt as temporary instructions you just wrote on a whiteboard in front of them.
That is a great analogy. So when I write a highly complex multi-page prompt with specific rules and edge cases, I am not fundamentally plunging the neural network. I am not rewriting the weights.
Not a single weight is altered. You are just writing better, more specific instructions on the whiteboard.
Wow.
This is called the inference phase. The model reads the whiteboard, pushes that temporary data through its frozen existing weights, and generates an output.
So prompt engineering is a valuable skill, obviously.
Very valuable.
But it is crucial to understand that it does not teach the model permanent new information.
Exactly. Once your session ends and the context window is cleared, the whiteboard is wiped clean. The model reverts back to its exact base state, dictated entirely by its frozen weights.
If prompting doesn't permanently teach the model, we really have to look at the process that actually sets those frozen weights in the first place.
You mentioned months of computation earlier. In the literature, we see two distinct phases of this: pre-training and fine-tuning.
Right.
From an infrastructure perspective, these are vastly different operations, aren't they?
Extremely different. Pre-training is the brute force foundational education phase.
The brute force phase. Imagine building a massive supercomputer cluster with thousands of GPUs running 247 for months, crunching petabytes of raw internet text.
Sounds expensive.
Very. The goal of pre-training is simply to teach the neural network the fundamental statistical patterns of human language, basic logic, and general world knowledge.
What do you get at the end of that?
The output of this massive expenditure is what we call a base model. It has incredible broad knowledge, but it's totally unstructured. It honestly just wants to autocomplete text.
So a base model is essentially the most educated, expensive autocomplete engine in the world at that stage. It doesn't actually know how to follow formatting instructions or act like a helpful assistant.
Exactly. If you ask a base model a question, it might just generate another related question instead of answering it.
Right, because it's just auto-completing. So to make it useful, we move to the second phase, fine-tuning.
Yes. This is specialization. It requires a tiny fraction of the compute power compared to pre-training. Maybe just a single GPU for a few hours.
Oh, that's way more accessible.
Yeah. You take that massive generalized base model and you train it further on a much smaller, highly curated data set.
Like what kind of data?
You show it thousands of specific examples of a human asking a question and a human providing a structured, helpful answer. By slightly adjusting the weights during this fine-tuning phase, you align the model's behavior.
You turn the raw autocomplete engine into a specialized assistant, or a dedicated Python coder, or a medical document analyzer.
Well, exactly.
That makes the distinction really clear. Pre-training builds the foundational brain. Fine-tuning shapes the behavior.
Spot on.
But even with all that rigorous training, the most notorious problem developers face when integrating these models into real apps is when they constantly output completely fabricated information.
The dreaded hallucination.
We call it hallucination.
Yeah.
But logically, if the model has 70 billion parameters of knowledge, why does it lie?
It's vital to drop the assumption that a language model is a database. It is not executing a SQL query to retrieve a stored verified fact.
Right.
It is fundamentally a probabilistic generation engine. It calculates the mathematical probability of the next token based on the sequence of tokens that preceded it.
So hallucination occurs when we treat predictive text on steroids as a factual lookup table.
Yes. If the model is prompted for information that wasn't strongly represented in its training weights, it doesn't have a built-in mechanism to just return null or, I don't know.
It just continues the statistical pattern.
It just keeps generating the next most likely tokens. The result is a grammatically perfect, highly confident string of text that is entirely fictional.
It's generating what mathematically sounds like a correct answer without any actual grounding in factual reality.
Exactly.
So how do we mitigate that? One technique heavily documented is leveraging zero-shot or few-shot prompting to guide the probabilistic engine.
Yes, and this taps directly into the concept of in-context learning.
What's zero-shot?
Zero-shot prompting is when you pass an instruction to the model with absolutely no prior examples. You provide a payload lake, extract the names from this text.
So you are relying entirely on the model's pre-trained weights to just magically understand the concept of name extraction.
Right. But few-shot prompting is an engineering technique where you inject a few structured examples right into the context window before your actual request.
You literally write examples on the whiteboard.
Yes. You provide a dummy input string and the exact desired output format 3 or 4 times.
In Python terms, you are essentially establishing a strict pattern in the array of tokens so that when the transformer runs its attention mechanism, it heavily weighs the pattern of your examples when generating the final tokens. You are conditioning the probability distribution.
Exactly. You are severely restricting the mathematical pathways it can take. This drastically reduces the chance of hallucination by forcing it to adhere to the rigid pattern you established on the whiteboard.
That makes sense. And if we want to directly manipulate the math behind those probability distributions, we touch the API parameters, specifically temperature.
Temperature. What's fascinating here is what it's actually doing to the math.
We often casually call it the creativity dial, but mathematically, what is it actually doing to the model's outputs?
Temperature modifies something called the softmax function. This is the final mathematical step before the model outputs a token.
The softmax function.
Yeah. When a model predicts the next word, it actually generates a massive list of probabilities for every possible token in its entire vocabulary.
So it ranks them.
Right. Token A might be a 90% probability, token B might be 5%, token C is 1%, and so on. If you set the temperature to a very low number, close to 0,
You're instructing the math to be ruthless.
exactly, it will almost exclusively pick the absolute highest probability token every single time. The output becomes highly deterministic, factual, and rigid.
It becomes a very predictable, kind of boring function.
Yes, but if you increase the temperature toward 1.0 or even higher, you mathematically flatten that probability curve.
Flatten it, meaning the lower probability words suddenly have a better chance of being picked.
You're instructing the model to occasionally sample from the lower probability tokens. It introduces controlled randomness.
Which is why a high-temperature model can write creative poetry or generate diverse code solutions.
And why it will give you a completely different sequence of tokens if you run the exact same script twice.
That summarizes the understand stage perfectly.
I think so too.
We use the transformer's attention mechanism to parallel process the embeddings in our context window. The layered neural network pushes the data through its fixed, pre-trained weights, reacting dynamically to the temporary prompts on the whiteboard. And we manage its probabilistic nature to avoid hallucinations using few-shot techniques and adjusting the mathematical temperature. We now have a functioning intelligent engine. But a brilliant, heavily trained model sitting as a massive file on a developer's hard drive is completely useless to a business.
Completely useless.
We have to make it accessible. We have to plug it into our Python apps, our web interfaces, and our data pipelines. This brings us to the third and final stage of our framework, serve.
Serve. Make it work in real life.
This is where AI moves from theory to traditional software engineering.
And this is exactly where the infrastructure reality hits developers really hard. The absolute first concept we must clarify here, because it strictly dictates server architecture and compute costs, is the hard division between training and inference.
We touched on this briefly, but let's formalize it. Because if I am deploying a web app, I need to know exactly what compute operations my servers are executing when a user clicks submit.
When you are training a model, you are running an incredibly heavy mathematical process called backpropagation.
Backpropagation.
The system is constantly calculating errors, calculating gradients, and updating those billions of weights. It requires massive clusters of GPUs and astronomical amounts of electricity.
Studying for the exam.
Exactly. But inference, however, is a one-way street. It is the forward pass only.
Just answering the exam.
Right. When a user sends a prompt, the data flows through the frozen neural network layers to produce an output. No weights are updated, no gradients are calculated. The model is not learning during a live chat.
Which means the computational cost of inference, while still heavy compared to traditional web requests, is orders of magnitude cheaper than training. You aren't studying, you are purely running inference, just reciting the answers based on what you already learned.
Exactly.
So what does this all mean for us? How do we actually bridge the gap between our standard Python web application and this inference engine running on some heavy GPU server?
That relies entirely on standard web protocols. We use an API, an application programming interface, and the process of deployment. Deployment is simply the DevOps act of taking the model's massive weight files, loading them into the VRAM of a remote GPU server, and wrapping them in web-serving software, often something built in Python, like FastAPI.
And once it's deployed?
Once it is deployed and listening, the API acts as the messenger, or a waiter, carrying your order from the app to the kitchen, which is the model, and bringing the food, the response, back.
It's just the standard client-server model. The client, our app, uses the Python requests library to send a JSON payload containing our prompt and our temperature settings. The API receives it, hands it to the inference engine, waits for the parallel processing to finish, and returns the generated tokens back to our app as a JSON response.
The pipeline is exactly that simple. But executing it efficiently at scale is where the real engineering challenges lie. Because in production, user experience is entirely governed by speed.
Which introduces latency and monitoring.
Right. In traditional web development, latency is just the time it takes for a database to return a query. In AI engineering, latency is much more complex.
We usually track two specific metrics here, time to first token and tokens per second.
Exactly. Time to first token is the initial delay. It's the time it takes the massive transformer to process the entire context window, your entire prompt, and spit out the very first generated word.
And if you have a massive prompt, that initial processing phase can take seconds.
Which feels like an absolute eternity to a user staring at a screen.
Right. And then once that first token drops, the generation speed tokens per second takes over, as the model sequentially predicts the rest of the response.
Lower latency equals faster answers.
And as an engineer, you absolutely cannot just deploy the endpoint and walk away. Monitoring in an ML environment is not just about checking if the server is up or how much memory it is using. It is fundamentally about tracking costs and keeping a watchful eye on performance over time.
Oh, the costs. If you accidentally write a Python script that gets stuck in an infinite loop making API calls to an inference engine.
You aren't just crashing a server.
No, you are burning thousands of dollars in GPU compute time. I have seen production teams accidentally rack up five-figure bills over a single weekend because they lacked proper endpoint monitoring.
That's a nightmare. But beyond just operational costs, you have to monitor for something much more insidious. Model drift.
Model drift.
This is a fascinating concept to me because it highlights the fundamental limitation of those frozen static weights. What happens when the underlying data of the real world changes, but the mathematical brain of the model remains frozen in time?
That is the textbook definition of model drift. You can have a flawlessly engineered deployment architecture, zero downtime, perfect latency, but the model's actual utility degrades.
Give me a real-world example of that.
Okay, suppose you spent millions training a highly specialized model to optimize global shipping logistics based on data from 2018 to 2019. The model learns the exact statistical patterns of global trade routes.
Okay.
Then, a massive global event occurs. A pandemic or a major shipping canal gets blocked. Supply chains are fundamentally rewritten overnight.
But the model is only running inference. It isn't learning from the new API requests. It doesn't know the world changed.
Exactly. The real-world statistical distribution drifted away from the training distribution. The model will confidently output shipping routes that are now mathematically disastrous. The performance plummets because it hasn't adapted.
So recognizing that your model is suffering from concept drift requires sophisticated monitoring pipelines that constantly evaluate the model's outputs against new, verified ground truth data.
Right.
Which means we need a systematic way to detect that drift, gather the new data, spin up the massive compute clusters to run backpropagation and update the weights, and then seamlessly deploy the newly fine-tuned model to the API endpoints without disrupting the users.
It's a massive cycle.
Managing that entire complex life cycle is the domain of our final overarching concept, MLOps.
MLOps. It's machine learning operations. It takes the established principles of DevOps continuous integration and continuous deployment and applies them to the unique challenges of massive floating point arrays and probabilistic engines.
It's treating ML like production software.
Exactly. It is the shift from a data scientist running a local Jupyter notebook on their laptop to an enterprise engineering team running automated pipelines. MLOps governs the version control of datasets, the automated orchestration of retraining runs, the regression testing of new models, and the zero downtime deployment to the inference servers.
It is the connective tissue that makes the entire serve stage possible at scale.
Managing training, deployment, monitoring, and versioning, all in one continuous cycle.
We have successfully traversed the entire master pipeline. This is the complete mental model for how modern AI actually functions from the raw string input to the final production endpoint.
Represent, understand, serve.
Exactly. We start with represent. We take Python strings, chop them into integer tokens, map them to dense 1,536-dimensional arrays called embeddings, and load them into the constrained bounds of our context window. Next, we understand. The transformer architecture uses self-attention matrix math to parallel process the relationships between those embeddings. The layered neural network pushes that data through its frozen pre-trained weights, reacting dynamically to the temporary prompts on the whiteboard. We mitigate hallucination by shaping the probability distribution with few-shot examples and manipulating the softmax temperature.
Perfectly summarized.
Finally, we serve. We acknowledge the divide between heavy training and lightweight inference. We wrap our deployed models in an API, tracking crucial latency metrics like time to first token. We establish rigorous monitoring to catch the silent failures of model drift, and we manage the entire lifecycle with robust MLOps pipelines. Every complex paper you read and every API documentation you study perfectly slots into these three distinct buckets.
It's an incredibly powerful framework. When you internalize the underlying mechanics that we are just manipulating vast matrices of floating point numbers through sequential stages, the entire field loses its mystique and simply becomes an incredibly fascinating software engineering challenge.
Let's prove how demystifying this framework actually is. We're going to do a rapid-fire translation drill.
Oh, I love these.
I will throw out a piece of intimidating, dense AI engineering jargon from the literature, and you translate it into plain mechanical English using the mental model we just broke down. Ready?
Ready.
Jargon number 1. We deployed a transformer with temperature 0.8.
Translation. We set up a server running a context-aware neural network that processes all the input data in parallel, and we adjusted the mathematical output dial to be slightly more creative and randomized with its vocabulary words.
Spot on. Jargon number 2. The model exceeded the context window.
Translation. The input list of tokens was physically larger than what the architecture can remember in its active memory at once, causing the oldest data to fall off the desk and be forgotten.
Perfect. Jargon number 3. Prompt engineering improved output.
Translation. We didn't alter the billions of underlying weights or change the model's actual brain. We simply rewrote the temporary instructions on the whiteboard to better constrain its probabilistic generation.
And the final jargon, number 4. We monitor drift in production.
Translation. We continuously track the live API endpoints to see if real-world patterns have changed away from the original training data, which would affect our AI's accuracy and performance.
Absolutely brilliant. Now that you have the complete mental model of how AI works from end to end, from the theoretical math down to the MLOps deployment pipelines, in our next lesson, we are going to open up our Python environments.
Time to write some code.
Yes. We'll take these very concepts and write our first Python script using the request library to connect to a real AI API endpoint, configure our JSON payloads, and move from architectural theory directly into executable code.
It's going to be a great session.
We encourage you to try the exercise of explaining these pipeline concepts to a friend or a colleague using your own Python analogies. Write any questions you have about the architecture in the comments below, and don't forget to like, share, and subscribe to keep building your AI engineering skills with 60 Seconds Academy.
As we wrap up this deep dive, here is a final architectural paradox for you to mull over.
Let's hear it.
If an AI's memory is just a temporary disk constrained by quadratic scaling costs, and its brain only learns when we explicitly pause everything for an expensive offline fine-tuning run, how might future engineers design entirely new architectures?
Wow.
How do we build systems that genuinely learn and dynamically adapt from every single conversation in real time without catastrophically forgetting the past? The future of AI engineering might just require breaking the very mathematical framework we learned today.